A half-mile wide rock just showed us that everything we assumed about how our solar system operates might be mistaken. Not slightly mistaken, fundamentally mistaken. And the wildest part? NASA wasn't even trying to find it. They were just doing a test run. Let me walk you through one of the most stunning chains of discovery in recent space exploration history. Discoveries that began with a warm-up flyby nobody was supposed to pay attention to, and ended with scientists completely rewriting the rulebook on asteroid science. This is the story of NASA's Lucy spacecraft and what it uncovered out there in the dark. First, let me explain what Lucy actually is, because this mission is unlike anything NASA has ever attempted. Lucy launched on October 16, 2021, from Cape Canaveral. Its name comes from a famous fossil, a 3.2 million-year-old skeleton of an early human ancestor found in Ethiopia in 1974. That fossil was named Lucy. And just as that fossil gave researchers an unexpected glimpse into human origins, this spacecraft is meant to give scientists an unexpected glimpse into the origins of our solar system. The reasoning is elegant when you consider it. Asteroids function like time capsules. They've barely changed in billions of years. They preserve the chemistry, the structure, the physical conditions from the earliest days of our solar system, back when planets were still being built from dust and rock. Studying them is almost like reading a history book, not of a country or a civilization, but of everything. Now here's what makes the Lucy mission truly remarkable. It's set to visit 11 asteroids across a 12-year journey spanning roughly 4 billion miles. No spacecraft in history has ever tried to visit this many asteroids in one mission, and the primary targets are known as Jupiter Trojans, a group of asteroids orbiting the Sun in two enormous clusters, one ahead of Jupiter and one behind it, held in gravitational lockstep with the giant planet. These objects have never been visited by any spacecraft. Scientists believe they're ancient leftovers from the very formation of the outer solar system, primitive, unaltered, and packed with secrets. Lucy is headed there, but along the way it had a few stops planned, and those stops turned into something nobody anticipated. The first stop was an asteroid called Dinkinesh, and this is where things get wild. Dinkinesh was added to the mission late. It wasn't originally part of the itinerary at all. Scientists identified it as a possible target because Lucy would be passing near enough to observe it. They decided to use it as a rehearsal, a chance to test the systems Lucy would need once it reached its major destinations. Dinkinesh was picked precisely because it looked unremarkable, small, ordinary, a half-mile wide rock in the main asteroid belt between Mars and Jupiter, the sort of object you use to test your equipment before the main event. Nobody expected Dinkinesh to matter. On November 1st, 2023, Lucy passed by Dinkinesh at a distance of about 270 miles, close enough to capture detailed images. The spacecraft was moving quickly, so the encounter lasted just minutes. The science team back on Earth waited for the data, anticipating routine confirmation shots. Instead, they received one of the most astonishing images in planetary science history. Dinkinesh wasn't alone. Orbiting the tiny asteroid was a moon, a satellite, a small companion rock that had gone undetected by observations from Earth. Scientists quickly named it Selam, an Amharic word meaning peace, chosen because Dinkinesh itself translates to the marvelous one in Amharic. Both names tie back to the original Lucy fossil story. Discovering a moon around a small asteroid was already surprising. Binary asteroid systems do exist, but they're uncommon, and finding one during what was meant to be a routine test flyby was genuinely extraordinary. But then, more data arrived. The science team examined Selam more closely and realized they hadn't found a moon at all. They'd found something never before discovered in the entire history of space exploration. Selam wasn't one object. It was two separate rocky bodies that had gently pressed together and merged into a single unit orbiting Dinkinesh. Scientists refer to this as a contact binary, formed when two objects collide very slowly, without enough force to break each other apart, and instead stick together like two lumps of dough being pressed into one. What Lucy had found was the first confirmed contact binary satellite ever discovered orbiting an asteroid. A moon made of two moons fused together, circling a rock nobody thought was worth a second glance. This had never been witnessed before, not once, in all of human space exploration. Consider that for a moment. We've sent spacecraft past hundreds of objects in our solar system. We've visited the Moon, Mars, Jupiter, Saturn, Uranus, Neptune, comets, and dozens of asteroids. And in all of that exploration, no one had ever spotted a contact binary orbiting another asteroid. Lucy found one on its very first flyby, during what was just a practice run. But the story gets more complicated. When scientists analyzed the complete dataset from the Dinkinesh flyby, they discovered that Selam's formation was even stranger than anyone had guessed. Examining Dinkinesh itself, they noticed two distinct geological features: a long trough, essentially a scar running along one side of the asteroid, and a ridge running along its equator, like a belt of piled up rock around its middle. These two features told a violent story. Scientists determined that at some point in the past, Dinkinesh began spinning too fast. The leading explanation involves a process called YORP, short for Yarkovsky-O'Keefe-Zhevsky-Paddock. It's a subtle but persistent effect where sunlight strikes an asteroid unevenly, gradually altering its rotation rate over thousands or millions of years, like an invisible hand slowly spinning a top. When Dinkinesh's spin became too fast, roughly a quarter of its mass suddenly broke off. That break created the trough. The debris flew outward, some falling back to form the ridge, while some drifted into orbit, eventually gathering into two separate bodies that later drifted close enough to fuse into Salam, an entire miniature solar system born from one asteroid tearing itself apart. The paper detailing all of this was published in the journal Nature in May 2024, and it immediately drew enormous attention from the planetary science community. Researchers from institutions including the University of Maryland, the Southwest Research Institute, Johns Hopkins APL, and NASA Goddard contributed to the findings. The conclusion was unmistakable. Even the smallest, most seemingly unremarkable asteroids in our solar system can carry histories of astonishing complexity. And Lucy had proven it during what was essentially a practice session. Then came the second flyby, and this one, believe it or not, was even stranger. The asteroid is named Donaldjohanson, after the paleoanthropologist who helped discover and study the original Lucy fossil in Ethiopia. The naming carries a poetic logic. The spacecraft named after the fossil, visiting an asteroid named after the man who found it. But what Lucy discovered at Donaldjohanson in April 2025 was something nobody, not Donaldjohanson himself, not NASA scientists, not anyone, could have predicted. On April 20th, 2025, Easter Sunday, Lucy swept within 960 kilometers, roughly 600 miles, of Donaldjohanson, traveling at approximately 30,000 miles per hour. The spacecraft moved so fast, and the encounter window was so brief, that Lucy's instruments had to shut down automatically 40 seconds before closest approach to shield the cameras from direct sunlight. Even so, it gathered images and spectral data of remarkable quality. What came back to Earth over the following days rewrote the understanding of this particular rock. Start with its shape. Before the flyby, scientists knew from Earth-based observations that Donaldjohanson showed significant brightness variations on a roughly 10-day cycle, suggesting an elongated rotating object. They expected something lumpy and stretched. What they weren't fully ready for was just how strange the object's geometry turned out to be. Donaldjohanson is a contact binary. Like Salam, it formed from two separate bodies that collided and merged. But the way these two lobes connect is unlike anything scientists have seen. The neck joining them, the narrow bridge between the two halves, resembles two ice cream cones placed tip to tip and nested together. NASA described it exactly that way in its official announcement. Two nested ice cream cones in space. It measures roughly 8.8 kilometers long and about 4.4 kilometers wide, nearly the length of 100 football fields end to end. The asteroid formed approximately 155 million years ago, when a much larger object was destroyed in a catastrophic collision. The two resulting pieces slowly drifted back together under their mutual gravity and merged gently. Not a crash, but more like a slow, tender reunion of fragments from the same shattered parent body. Scientists from the Southwest Research Institute describe its geology as strikingly complex, featuring craters of varying ages and surface textures that record a long history of smaller impacts and changes. But the shape was only the beginning. The rotation of Donaldjohanson is what truly baffled the science team. Before the flyby, Earth-based telescopes had measured the asteroid rotating once every 10.5 days, slow for an asteroid, but otherwise unremarkable. What Lucy's data revealed was that this 10.5-day rotation told only part of the story. The asteroid was also undergoing a second, entirely separate wobble around its long axis, a tumbling motion repeating every 26.5 days. Combined, these two motions mean Donaldjohanson doesn't spin like a ball or a top. It tumbles through space like a football thrown by someone with no idea what they're doing. Scientists call this a non-principal axis rotation state, meaning the asteroid wobbles in a deeply unusual way. Most asteroids eventually settle into a single, stable spin. This one hasn't. It's caught in a state of perpetual physical confusion, rotating on two axes at once in a pattern existing models hadn't predicted. This finding was published in the journal Science on June 18, 2026, authored by Dr. Simone Marchi, Deputy Principal Investigator of the Lucy mission, and his team. The paper was clear about three major unexpected findings at Donaldjohanson: the strange two-axis tumbling rotation, the bizarre ice cream cone-shaped neck, and the third finding, the one that genuinely stunned everyone when the data came in: evidence of liquid water, or rather proof that liquid water had once existed there long ago. Lucy carries an infrared spectrometer, and when it was aimed at the surface of Donaldjohanson during the flyby, it detected something specific and extraordinary: iron-rich clay minerals. Clay minerals don't form from dry rock. They form when liquid water interacts with rocky material over time. Finding iron-rich clay on an asteroid in the main asteroid belt, one that formed only 155 million years ago and is barely half a mile wide, means that at some point in the history of its parent body, liquid water was present. Not just ice, not just vapor, actual liquid water existing inside a rocky asteroid somewhere between Mars and Jupiter. To grasp why this matters so much, consider where Earth's water came from, one of the biggest open questions in planetary science. Earth formed in the inner solar system, where temperatures were too high to retain volatiles like water. So how did Earth end up covered in oceans? The leading theory holds that water was delivered to early Earth through impacts, asteroids, and comets, carrying water from the colder outer solar system that collided with our planet billions of years ago. The composition of Earth's oceans closely resembles what scientists would expect from certain water-bearing asteroids. Now, Lucy has found direct evidence of water chemistry on a main belt asteroid, meaning water-bearing material was present and active in the asteroid belt, close enough to Earth's neighborhood to have possibly contributed to our oceans. Scientists compared the clay minerals on Donaldjohanson to those found on other asteroids. When NASA's OSIRIS-REx mission visited Bennu and Japan's Hayabusa 2 mission visited Ryugu, both also found clay minerals. But the clays on Bennu and Ryugu are magnesium-rich rather than iron-rich, suggesting those asteroids retained liquid water for much longer, possibly millions of years, while still part of larger parent bodies. The iron-rich clays on Donaldjohanson point instead to a much briefer water episode, a fleeting burst of liquid water chemistry inside its parent body before that parent was destroyed. And because Donaldjohanson itself formed only 155 million years ago, far younger than Bennu or Ryugu, which are 1 to 2 billion years old, it may represent an entirely different chapter in the story of how water moved through the early solar system. These differences suggest that the parent bodies of Bennu, Ryugu, and Donaldjohanson likely formed in different regions or at different times before migrating into the main belt over billions of years. Each is a chapter in the same book. Now pause and consider what Lucy has accomplished. It has completed 2 asteroid flybys. Both were supposed to be warm-ups. Both produced discoveries that were, in their respective categories, genuinely unprecedented in human history. A contact binary satellite and a wobbling, double-lobed asteroid carrying ancient water chemistry. And both were merely the practice rounds, the opening acts. The real mission, the Jupiter Trojans, hasn't even begun. Lucy will reach the Trojan asteroid swarms in 2027, and everything about what those asteroids might look like or contain remains a complete mystery. No spacecraft has ever visited a Jupiter Trojan. Scientists have theoretical models, but models aren't the same as reality, as Lucy has already proven twice. The Trojans are thought to be among the most primitive objects in the solar system, darker, richer in carbon, possibly holding organic molecules that predate Earth's formation. Some scientists believe they may have originated in the outermost regions of the solar system, far beyond Neptune, and were gravitationally captured into Jupiter's orbit during a period of massive solar system reorganization billions of years ago. If true, they're essentially messengers from the most distant and ancient corners of our cosmic neighborhood. Lucy will visit at least 6 of them between 2027 and 2033, including members of the Euripides family, a collisional cluster of asteroids believed to share a common shattered parent, as well as Patroclus and Menoetius, a rare near-equal mass binary pair, 2 similarly sized rocks orbiting one another. Each target represents something distinct, carrying its own piece of the early solar system story. And given what Lucy has already uncovered at what were supposed to be unimportant warm-up stops, the scientific community is watching closely. The principal investigator of the Lucy mission is Dr. Hal Levison of the Southwest Research Institute in Boulder, Colorado. After the Donaldjohanson flyby, he made a comment worth repeating. He called the warm-up asteroids proving to be quite interesting in their own right. That's the scientific understatement of the decade. These weren't meant to be interesting. They were meant to be rehearsals. Yet both produced discoveries that will be cited in scientific literature for decades to come. There's something deeper worth sitting with here. We live in an era where space exploration moves faster, achieves more, and produces greater results than at any earlier point in human history. Spacecraft are smaller, instruments more sensitive, and computers processing the data more powerful than anything available during the original space age. And yet, time and again, when we actually travel somewhere and look closely, the universe surprises us, not in minor ways, but fundamentally. Things assumed to be dull turn out to be fascinating. Objects thought simple turn out to be staggeringly complex. The solar system keeps proving stranger than our models suggest. What Lucy found at Dinkinesh shouldn't exist. A moon made of 2 moons, born when an asteroid tore itself apart under sunlight alone. What it found at Donaldjohanson shouldn't behave the way it does. A peanut-shaped, ice cream cone-necked rock wobbling on 2 axes, carrying the chemical fingerprint of ancient liquid water, formed just 155 million years ago in a belt of debris between two planets. Both discoveries occurred at targets the mission had essentially treated as afterthoughts. And the actual targets haven't even been visited yet. This is why missions like Lucy matter. This is why spending billions of dollars to send a spacecraft on a 12-year, 4 billion-mile journey through the solar system makes sense. Not because we know what we'll find, but precisely because we don't. Every time humanity has pointed an instrument at something new, close enough to observe clearly, the answer has turned out to be more complicated and more fascinating than the question asked. Lucy is examining things no instrument has ever reached, in a region of the solar system nobody has ever visited, studying objects that have sat in the dark and cold for billions of years, entirely unchanged, waiting. And based on what's already been found, the double moon that shouldn't exist, the wobbling peanut defying our models, the ancient water chemistry preserved in iron-rich clay on a rock born from a catastrophe 155 million years ago, the smart bet is that when Lucy reaches the Trojans in 2027, it will uncover something none of us expected. The mission is already among the great scientific journeys of the 21st century, and it's only just getting started. Lucy is out there right now, moving through the main asteroid belt at more than 30,000 miles per hour, heading toward Jupiter's gravitational neighborhood, carrying instruments tuned and calibrated by everything it has already learned. Teams at the Southwest Research Institute, NASA Goddard, Johns Hopkins APL, and Lockheed Martin track it every single day. Every data point returned is another piece of the solar system's biography. Every new image is a page from a book no one has ever read. We know the solar system formed 4.6 billion years ago from a swirling cloud of gas and dust. We know it passed through periods of violent chaos, giant planet migrations, catastrophic collisions, and gradual settling into the relatively stable arrangement we see today. But we don't know all the details. We don't fully know where different materials formed, how water traveled through the system, or how the building blocks of Earth and the other rocky planets came together. Lucy is out there searching for those answers in the oldest surviving evidence, the asteroids that watched it all unfold from a front row seat, holding their secrets ever since. A half-mile-wide rock in the middle of the asteroid belt just told us that liquid water once existed inside it. That shouldn't happen. It's too small. It's too young. It's in the wrong part of the solar system. And yet, the chemistry is right there, locked in iron-rich clay on its surface, undeniable and waiting to be understood. That's the kind of discovery that rewrites textbooks. That's the kind of discovery that forces scientists to question their assumptions and rebuild their models from the ground up. And that's exactly what great science looks like. Not confirmation of what we already believed, but a door swinging open into something we never expected to find. Lucy is on its way. The Trojans are waiting. And whatever is out there has never before been seen by human eyes. Stay curious, because the universe is stranger than you think. And right now, NASA is heading straight into the strangest part of it.